Hi, my name is Mitchell Lord, and this is my Lab 3. As an introduction, the purpose of this lab was to analyze gravitational motion of outer space bodies using a computational model in Newton's second law. In the first part of the lab, I analyzed the motion of a star orbiting a black hole and used the data I got from that to estimate the mass of the black hole. In the second part, I created a simulation of a spaceship moving under the gravitational influence of a planet and its moon. Here's a brief preview of my results from part 1. I estimated the mass of the black hole to be about 1.22 times 10 to the 34 kilograms. Here's a brief preview of my results from part 2. I used this initial velocity to achieve this orbit in the second part. The physics principles used in this lab were Newton's second law, F equals ma, and we used this to calculate the force acting on the bodies and update their positions and velocities. Also used the universal law of gravitation, which was used for the star and the black hole interaction, the planet and the moon interaction, and the spaceship's interaction with both the planet and the moon. And we also used the formulas for parallel and perpendicular components of force. So we decomposed the force into its parallel and perpendicular components. Here are the equations used: Newton's second law, F equals ma, the position and velocity update formulas, the law of universal gravitation. We also used the equations for the perpendicular and parallel components of the force. In the first part, the system is the sun orbiting the black hole and the surroundings of the black hole itself. And here are all the initial conditions. So here's my code for part 1. Here's the initial properties and conditions. Here's the main calculation loop where we calculate the velocities, momentums, their changes, the change in momentum, which is the net force according to Newton's second law. And then we calculate the p-hat vector, which is just a unit vector in the direction of momentum. We use that to decompose the force into its parallel and perpendicular components to display it in the output, and then we rearrange the universal law of gravitation to compute the mass of the black hole at every step. I estimated the mass of the black hole at every step using this equation, which is just a rearrangement of the universal law of gravitation. And then at the end, when I averaged all the masses out, I got 1.22 times 10 to the 34 kilograms. Here's a video of the output of my code. So as you can see, there's the perpendicular and the parallel components of the force. Moving on to part 2. In this part, the system is a spaceship and the surroundings of the planet and its moon. Here are all the initial conditions, the masses, and the positions. And here are the initial velocities. Here are some snippets of my code from part 2, including the initial conditions on the left, and on the right is the initial velocity that I used for my ship to get the orbit. Here's the main loop of my code. So in this, we just calculate the net forces of gravity acting between the three masses, between the planet and the moon, between the ship and the moon, the ship and the planet, the moon and the planet. And we use all that to calculate the net force and use Newton's second law to update the velocity and the position. And here is a video of my output. So as you can see, the moon and the spaceship are interacting with each other, and the spaceship is also interacting with the planet in the center. So it's about to break off from the moon's orbit here. Yeah. So it orbited the moon for one orbit around the planet, and then it breaks off and starts orbiting the planet itself. So I got this weird looking orbit using this initial velocity, and as you can see, the spaceship completed an orbit which was influenced by both the planet and the moon's gravity without crashing. Possible sources of error in this lab include finite difference approximation, which is just approximating the derivative of momentum with just the change in p over the change in t, which could cause some numerical error. There's the discrete time steps. It wasn't continuous. We assume in part 1 that the star is only influenced by the black hole. Any additional influences were neglected. And in part 2, we somewhat simplified the model. So what does it mean? What are the differences between the net force and the rate of change of momentum? So the rate of change of momentum describes how an object's momentum changes over time, and it's determined from the observed motion. The net force is the physical cause of that change in momentum. And according to Newton's second law, the net force on an object is equal to the rate of change of momentum of that object. And the parallel component changes the magnitude of the momentum, and the perpendicular component changes the direction of momentum. What if we were to include the black hole in the calculations for part two? So in this system, I would just include all the gravitational interactions between all the different masses in the system. The black hole and star would dominate the large scale motion because of their big masses. Planet moon interaction would dominate the moon's orbit, and the planet spaceship and moon spaceship interactions would dominate the spaceship's motion. Thank you.